something that we don't do much in the lab anymore, and I'm really disappointed by it because it was, for me as a high school chemistry student, one of my favorite things to do, and that was work with glass, bend glass into different shapes, and make different kinds of equipment and apparatus. When I took chemistry, the first lab we did, we involved making right-angle bends, U-tubes, capillary tubes, etc., which then later on we discovered would allow us to take all of our glass stirring rods and bend them into various shapes that were kind of cool but made them essentially useless. But you know, learning how to handle glass and bend glass was one of the neat things that we did. And again, something I really remember from high school chemistry. Most of that stuff has vanished from chemistry courses now, and I think it's unfortunate. And so when I spot something in a lab where there's a chance for my students to make a piece of apparatus that they can use later, I try to bring that back in and give them a chance to make their own rod, stirring rod, or piece of glass tubing that's got at a right angle or whatever it might be. And we're going to take a look at making a U-tube first of all, and then we'll use it later in an experiment, in an electrolysis experiment. I'm going to take a small piece of glass, I don't know how long that is, about that long, and I'm going to show you how to do it. Now this part right here is in itself fairly amazing. My suspicion is, and in fact my knowledge is, having worked with a lot of young teachers in the last few years, is that there are a lot of schools where these things are in drawers and in beakers and in containers, and people are looking at them going, what is that? What's it good for? I've got all these funny looking kind of funnel shaped affairs sitting in a drawer in a beaker, and I have no idea what to do with it. These are flame spreaders, and really these are the things you should be using when you're bending glass, particularly if you want to make a U-tube. Now, if you don't have one of these, you can still do it. It doesn't really make that much difference. But if you've got some wing tips, or is that what they're called? Wing tips? I believe so, yeah. And if you've got one, put it on top of your Bunsen burner. Hopefully it'll fit, unless they were bought for a different size. And you can slide it on top and use it. So what I'm going to do is light the burner. That in itself will amaze your students, because you can make your Bunsen burner light on the first try. It takes them 15 or 20. And then I'm going to take this tube and I'm going to slowly rotate it back and forth. Usually because I'm left-handed, I'll rotate with my left hand. And then on my right hand, all I'm doing is just really hanging on to the edge of this thing and not holding it tight at all. It's just a place for the stuff to pivot back and forth. You'll notice something happening now, and actually when the glass starts to get softer and gets ready to melt or be bent, it'll start to give you this yellow color. You can kind of see that flame now, before when it was in the flame, and you can see how it's sagging. Once I get it to that point, it's that quick. I'm going to do that again, just so you can see it, and make a second one of these, a valuable thing to learn. These are very hot right now. If you set it down on the tabletop, there's a good chance it'll burn the tabletop. And so I'm going to make one more. And go back here and come back again, rotating it quickly. It'll be starting to get soft when I see that yellowish flame. There's that yellowish flame. That's actually sodium boiling off in the soft glass. It's a sodium compound that's in there. Now you can see that it's actually starting to sag. This time I'll try to bend it in front of the Bunsen burner so it might be easier for the camera to see what happens. I'm not in the center, so this one's going to be interesting. And bring it around like that. And then it'll stay soft for a short period of time. You can see it's still bending. At some point it gets to be rigid. Where it's bent, that's a weak spot. And if you put much pressure on this thing, it will crack at that weak spot, because what you've done is you've stretched the glass in that point to bring it around and make it in a curve. The second one wasn't quite as good as the first one, and that's my own fault for not paying attention to where I was heating it, and I didn't heat it in the center. When your students make these, some of them will actually turn out to be U-tubes. Some will turn out to be any combination of shapes that you can imagine. The only thing that really has to be true is that they don't pull it or stretch it to the point of where at the bottom down here, it seals, in which case there's not going to be any travel through the middle of it. Well, that's preparation of a U-tube. These have already been fire polished on the end. That would be something else I would teach the students how to do. Fire polish the end of it so it's not sharp, but I'll set this aside. And now we want to take a second to look at what we can use these U-tubes for. My first year of teaching, I finished the textbook. I got through every single chapter in the book. I learned an enormous amount of chemistry. I'm not real sure if my students learned anything, but I learned an enormous amount of chemistry. And I learned about things that I wanted to do the next year and things that I didn't want to do the next year. One of the things that I was 100% sure I didn't want to do the next year was any electrolysis experiment. The days that we did electrolysis experiments involved my going over to the physics classroom, borrowing these gigantic battery packs that they had, getting alligator clips, big chunks of wire, and bringing them back over to my classroom and attempting to set them up so that my students could put the electrolysis apparatus together. I spent my entire laboratory period running around making sure the alligator clips worked, that they were connected correctly, that the fuses in the battery packs hadn't been all blown, because once you touch the alligator clips together, which every kid did, then of course it blows the fuse in the battery pack, so then I had to have like thousands of fuses to replace all the time, because once you blow the fuse, then of course you're going to see how many times you can blow it. Actually, it's interesting, you only blow it once, but then when the teacher comes back and puts a new one in, you can blow it again. And I remember walking out from the electrolysis lab and walking back and sitting down at my desk and just kind of looking at it and going, never again. I may do this as a demonstration, but I have no intention of ever doing it as a student lab. In the last few years, there's been a move in chemistry to go to smaller scale stuff. And one of the great things about small scale stuff is that we've been allowed to do some things that we couldn't do before because the apparatus was too big, too complicated, too hard to set up. With small scale, we can go to some really tiny setups with very simple apparatus. What I have here is the apparatus I'm going to use for electrolysis. It consists of a U-tube, a student-made U-tube, a 9-volt battery. That 9-volt battery has a battery cap on top of it. And then connected to that are a couple of alligator clips, and I've got a couple of carbon electrodes there, which turn out to be, of course, just pencil leads. All of that stuff, quite inexpensive. You can put the whole apparatus together for next to nothing. The total cost of an electrolysis setup with a battery pack and alligator cables and a giant U-tube, couple $100. This is something every kid in my class can do. This is something that if it breaks, falls apart, I've lost essentially nothing. So it's a really nice setup in that respect. Same kind of deal that we've looked at before. Now, what I want to do is I want to take a look at electrolysis of potassium iodide, KI. The chemistry here is pretty elegant and fairly complicated. I kind of approach this two different ways. I feel very comfortable allowing every level of chemistry student we have do this electrolysis experiment and then gauge the depth that we go into based on what we're really trying to get across to them. With honors level or with AP students, we're going to be talking about E0 values and cell potentials and all kinds of things like that. With a group that really doesn't need to worry about E0 values, we're going to take this and look at it as oh wow, look what can happen when you run an electric current through a liquid. Look at the kinds of things you can produce. Look at the chemicals that are generated. Electrolysis is a very common way that chemicals are produced industrially. There are lots of things that are done by electrolysis. So let's take a look at this and look at the simplicity of the whole process. I have the system set up here. I'm going to take some potassium iodide in a transfer pipette and just shoot it down inside the U-tube. I'm going to make sure that there's no air bubble blocking it off. I'm going to leave, that's about right. That's about the right amount. Okay, so now what we've got is the system. There's KI, it's about half molar, and it's down inside there. I've got my carbon electrodes, again, just pencil leads. I suppose you could go out and buy real carbon electrodes if you wanted to. Can't imagine why you would do that. And now I'm going to drop those electrodes down inside here. And the only thing I need to be careful of is that they don't touch. This is so amazing. Look at this already. It's been in here how long? 5 seconds. And already over at the electrode on the, let's see, my right, I'm seeing some reddish brown solution be produced. On the other side, I'm getting some bubbling. How long did that take? It took like no time at all. I mean, the reason that you might want to have your students make their U-tubes, the lab will be over in 10 minutes. You got to kill another 40. So, I mean, that's really cool. And here we can see the bubbles here. They're forming. Now, the question comes to mind, what actually is going on in there? And the chemistry is really pretty elegant. We can get some hints about what's going on there if we throw a couple of indicators in here. And I'm going to put a drop of starch solution in the side where the red-brown is. And there we go. I seriously doubt you can tell what color that is. I imagine it looks like it's black. It looks like it's black to me, but I'm going to say it's blue. Almost every kid I have in class knows about starch and iodine. They do it in elementary school. They drop iodine on pieces of potato. They do it in their biology classroom. So when they come into chemistry and I put that drop down inside there, they look at that and go, hey, that's iodine in there. That's the starch iodine test that's being produced there. So on this side, I'm getting iodine being generated. Now, if you want to get really serious about it, that reddish brown stuff down there is probably I3 minus ion dissolved. It's not really iodine. It's probably not I2. There is an equilibrium going on in here between I3 minus and I2. I don't know how serious you want to get about that, but that's the chemistry that's going on there. Now, on the other side, I'm going to put a drop of phenolphthalein and take a look at that. Oh, and look at that. Wow. Nothing more exciting than watching phenolphthalein turn pink. And it's just so great. You can move it around a little bit, and there's the pink color. Phenolphthalein tells me, and again, in theory, my students, by the time I get to this, we've been through acid-base chemistry, so they know phenolphthalein turns pink in a base. So they're going to look at this thing and say, hey, there must be hydroxide ion there. So what I've done now is, let's take a look at what's going on inside there. What actually have I got in here? I've got a potassium iodide solution. That's Ki. The species that are present in there, in the solution, are potassium ion, K+. I've got I- iodide ion, and I've got water. I'm going to kind of ignore the equilibrium between water and hydroxide and hydrogen ion that goes on. It's there. There are some hydrogen ions, there are some hydroxide ions, but I'm going to sort of forget about those and not worry about it. On this E0 chart over here, I've highlighted the three species that are present in the system. The iodine, the iodide ion, I should say, the water, and the potassium ion. And the question comes up, what's actually happening inside here? Why aren't I getting potassium at the one electrode instead of this bluish or this pinkish stuff that's over there in the bubbles. We know potassium's a metal. It's not bubbling off. And so the E0 chart really tells us that. And what I want to get through with the E0 chart simply is the idea that, hey, when I look at this chart, these reduction potentials tell me what things are easy to reduce, what things are hard to reduce. The easiest material to reduce is fluorine, F2 at the top of the chart. It's got the highest reduction potential. It's very easy to reduce. If I put F2 with just about anything, fluorine is going to get electrons from something else, rip them away, and convert to fluoride ion. And as I work my way down this chart, it gets more and more difficult to reduce the material. So by the time I make it to lithium ion, it's nigh on to impossible to get lithium ion to reduce. It's got the highest cell potential that's there. So I've got three things in my system. I've got I-, I've got H2O, and I've got K+. In nature, in chemistry, the simplest one is going to be the one that takes place. The one that takes the least amount of energy, the easiest path is going to be the path that it follows. So I've got a choice between water being broken down into hydrogen and hydroxide ion, or potassium ion being converted to potassium metal. It's easier for water to be reduced than it is for potassium ion. So in my system over there, this is the reaction that takes place. I have proof of that because I can see the bubbles. I have yet to figure out a way to test for the hydrogen. There's just not enough there. I mean, if I tried to ignite those bubbles, I'm not sure what would happen, but you'd get a microscale pop, which, you know, maybe if you had a hydrogen explosion trained dog might be able to hear, but it's not going to happen for people. So I've got that reaction, and I've seen the hydroxide ion because of the phenolphthalein and the bubbles for the hydrogen. I have no indication of potassium being generated there. So this is my one reaction. This is my reduction. Now, looking at it from the other side, what else is in there? The only other thing I have is iodine. If I've got something that's reduced, then there has to be something oxidized. You cannot have one without the other. There are no ox reactions. There are redox reactions. There's reduction and there's oxidation, and they have to happen together because if you're going to lose electrons, something else has got to gain them. There are not atoms out there, molecules, compounds, throwing electrons out trying to get rid of them. There has to be something to come in and say, I'd like to have your electrons. Fluorine, not very polite, comes in and sort of rips the electrons off, sort of the Tyrannosaurus Rex of the electron grabbing group. But in this case, I look up here and the only thing I've got in here is iodine. Iodine can be oxidized to I2. Well, in fact, I have proof of that over there in the test tube because I've done the starch iodine test. And it's the only other species I have in here. You might go, hey, how about water? Well, let's look where water is. It's harder to do. Because when I'm going back the other way, of course, it's more difficult working your way up. And so now I got iodine. It's easier to do than water. Kind of cool. It's neat chemistry. You've got proof positive. I will be honest, I have some great students. I had terrific students in some of my classes. I had every kid do this. And then later I set it up on a larger scale in front of the room and we kind of did what we just did right now. And I went through it again with them and tried to point out everything because there's so much chemistry going on here. So many different things are happening that it's very, very difficult for students to pick it up. I'm not sure how many years I taught before I had a real good handle on what was going on in an electrolysis reaction. And in fact, to be honest, I'm not sure I still have a real good handle on what's going on because some of the things still kind of baffle me when I look at them. What's neat about this is you can do potassium iodide and then you can try some other things. And I did sodium bromide, and I just set it up, and I'm going to set this right over next to it so you can take a quick look at it. This is sodium bromide, and I only let it run for a few seconds, but again, with the bromine, you're getting over on the one side, you can see the reddish-brown color. It looks very much like the iodine does, but in this case, it's a bromine being generated. And then on the opposite side, you get hydrogen. Once they've done that, if you want to really give them something that kind of boggles their mind, you can go the next step and give them one where eventually you get them convinced that the alkali metals aren't going to react. It's going to be the water, or the active metals aren't going to react. And then you can come back with something like zinc bromide or something of that sort. And I've had this one set up for a little while because it's a little slower. This one takes about 10 minutes to work. But you can probably see, I hope, yeah, I'll lift this up just a little bit so it's not behind the rubber band. On this electrode, instead of getting bubbles, I've got some shiny crystals. That's zinc plating out on the electrode. On the other side, because this is bromide, you can see more of the reddish color that we associate with bromine, dissolved in water, bromine water. There is, if you really want to get into it, a very slight halogen odor over the top of this. I mean, it's really slight. And if you do good lab technique and waft, you're not going to smell anything. This is one where you've almost got to stick your nose on top of the hole and, you know, snort it up, which is not a good idea because you can draw the stuff up out of here. The other thing that's neat about this, if it falls over, there's enough surface tension in here that the solutions don't leak out because it's such a small tube. So it's really kind of neat. So you can do that. One real quick addition to this. If you do, well, let's go back and look at the chart for just a second. Here's the zinc reaction, and notice where the water is. Water's a little bit harder to reduce than zinc is. So zinc goes before water does. And that's why I'm getting the zinc crystals on there. The thing I liked about using zinc as opposed to like copper 2 chloride, which is what a lot of people do, is that the zinc's right next to the water on my table. You know, it's like, hey, look, it's right there. You don't have to search for it. When I do copper 2 chloride, they're all over the chart trying to figure out where it's at. The one that's the real problem for most students is sodium chloride. When I do sodium chloride, I get hydrogen because it's not going to be the sodium. But I don't, and if I look up here, I'm figuring going backwards, the next easiest one should be water going back to oxygen. In fact, when I do sodium chloride, I get chlorine gas. And I can smell it. Chlorine is really distinctive when you do sodium chloride. And I have my students do that, and this is really an AP concept, because there is more to this than just the E0 value. There's something in their AP textbook that they call overvoltage. And it isn't just simply that you need 1.23 or 1.36 volts or whatever it might be to drive that half reaction as far as you want it to go. Some of the half reactions, because of the nature of the compounds that are involved and the way that they behave in solution, what kind of hydrates they form and that kind of stuff, causes you to actually need a little bit more voltage and over voltage to drive the reaction. It turns out that the over voltage for the water reaction is sufficient to put it above chlorine on this table. And so chlorine comes out. Now, how do you calculate that? Is that really important for your students to figure out? Only like once every 20 years they'll have a question about over voltage on the AP test. And it's usually worth like a half a point. It's probably not a necessity, but it's kind of a neat thing to look at, and if somebody asks you about it. Or that rare kid that when you do sodium chloride actually looks at the E0 chart and says, hey, Mr. Lewis, how come that didn't work the way all the other ones did? You got to have an answer. Beyond, the standard, it's magic, I don't know. I don't know is, by the way, a good answer. Because actually I don't know. It's the real answer for me right now. I have no idea why these go out of order, other than I read the book and it says overvoltage. And that's supposed to be a factor. I don't know what the factors are that really determine overvoltage. So what we've looked at here is a way for every kid in your classroom to do electrolysis so that they can see it up close, perform the reaction, and it's cheap. It doesn't cost you much of anything. 9-volt battery, the battery caps, the alligator clips, all of that stuff, quite inexpensive. You can put the whole apparatus together for next to nothing. The total amount of solution you'll need for the day, I don't know how many kids you have. I had about 130, which means I'd have 65 lab setups, roughly. 2 milliliters is way more than you need for that test tube. So a couple hundred milliliters of solution is going to last you a lifetime, or at least a school year. That's a really neat way to do electrolysis.